All right, today's lesson actually turned into more of an activity. So rather than recording during class, I'm just recording after the fact to walk through the notes and anything we talked about. So for anyone who is absent, here's what you want to know. Equilibrium is maybe one of my favorite topics in chemistry because once you understand how equilibrium works, it sort of redefines and opens up how all chemical things work. So just jumping into what the notes say, so far this year we've assumed that chemical reactions cease when all of the reactants have become products, so when everything runs out. What I mean by that is like we've even done limiting reactant. Whichever reactant is the least, that one runs out first and the whole reaction stops. This assumes, however, that the products never revert back to their reactants. We've even said that a chemical change is considered irreversible. Now, we've seen some very chemical-looking changes that were also very reversible, even in some of our labs this year. But in general, chemical changes don't seem to go backwards, except for how this next line says virtually all chemical reactions are actually reversible to some extent. If the whole world is made out of these little particles, right? So an H2O molecule, I've got all these little protons with electrons whizzing around them, and it is connected to two other atoms. This is my quick and dirty image of an H2O molecule. The only reason this H2O molecule exists is because these protons in the middle are attracted to these electrons, which is attracted to that proton, and so these various little orbs just happen to be near one another. And because we live in a messy world with lots of things moving around and things going crazy, it's not at all unreasonable to imagine that sometimes one of these hydrogens could just kind of like maybe accidentally fall off. We might not even know why. It just sort of could. Or in nuclear chemistry, we found that sometimes even like the protons in there could just sort of accidentally fall off, and then the whole thing explodes, right? And so the actual defining quality of all that exists and all that changes is probability. The reason that H2O molecule exists rather than falling apart is that it is more likely for those hydrogens to rest near that oxygen than it is for them to go anywhere else. And if we look at that probability idea, we can begin to understand more accurately how reactions work, when they stop working, and why they may or may not be reversible. So rather than saying a reaction is finished when all of the reactants have been used up, the better definition would to say a reaction is finished when the rate of the forward reaction equals the rate of the reverse reaction. When the rate of the forward reaction equals the rate of the reverse reaction. And we did an activity in class that you could probably find like virtual dice online, or if you just have a bajillion dice at home, you could try it yourself. But it's a way to try to wrap our minds around what this means. We're using the fairly simple chemical change of carbon dioxide dissolved in water forming carbonic acid. This is what happens in the soda that we drink. So that's this chemical formula right here. When CO2 combines with water, at least some of it will form carbonic acid, H2CO3. Carbonic acid is particularly unstable, and so it doesn't take much at all to knock that thing apart, and the H2CO3 will break back into its original carbon dioxide and water. So the better way to write this, fix my handwriting a little bit, is carbon dioxide plus water, and then we draw this little forwards-backwards arrow thing to indicate a reversible reaction, will form H2CO3, which can also break back into CO2 and H2O. Now, we don't use these reversible forward and backward arrows for every chemical reaction. Every chemical reaction is technically reversible, but many chemical reactions are so difficult to reverse or reverse so slowly or in such small amounts that they would not be noticeable, sometimes not even measurable. And so we reserve these arrows for things that are obviously, definitely reversing like before our very eyes. So what we did is imagine that you have a cup full of 50 dice, and those dice represent 50 carbon dioxide molecules. We poured them all into a container, and anything that had a 1, we took out of the container and put into a different container called H2CO3, effectively saying not all of the carbon dioxide will react, but some of it, about 1/6 of them, turn into H2CO3. And then we counted how many H2CO3 molecules we had. This is the ideal perfect graph. Nobody's data looked exactly like this, but it was the same shape. So it looks like, ideally, 1/6 of 50 is about 7 or 8. And so 7 particles of carbon dioxide turned into carbonic acid down here, which means I had about 43 left. So then, from now on, when we roll again, we roll all of the carbon dioxide dice, and we roll all of the carbonic acid dice, and anything that at all that gets a 1 is taken from its container and placed into the other container, which means some of this acid is going to be moved into the carbon dioxide container, and some of this carbon dioxide is going to be moved into the acid container. When you do that, you end up with still a little bit less carbon dioxide than you had, but not quite as huge a leap as before, and a little bit more carbonic acid. Then you keep doing this. You roll all the dice, all of the ones swap places. And as you do it, the amount of carbon dioxide continues to drop, and the amount of carbonic acid continues to rise until eventually it just sort of centers right around this middle line of 25 of each. And then we talked about, what does this mean? So the first question I like to ask is, did the reaction ever stop? And the answer is no. You can keep rolling the dice forever, and about 1/6 of 25 blue ones will turn orange, and at the same time, about 1/6 of 25 orange ones will turn blue. And so you'll just see these go that way, and 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 so on. And the line will continue to be 25 and 25. So technically, no, the reaction doesn't stop, but does the reaction finish? And I would say yes, because as far as anyone can tell, we have 25 carbon dioxides and 25 carbonic acids, and we always will have 25 of each. So that's how we answered this question. How did the rate of reaction of the forward reaction, carbon dioxide into acid, change over time? That rate decreased. I lost like 8, and then the next time I lost more like 7 or 6, and then the next time I lost like 5, and then the next time we lost like 3, and then 2, and then 1, and then 1, and then 1, and then we didn't really lose any anymore. The reason why it decreased with our dice is I roll 50 dice and then I take some of the way, and so the next time I roll fewer dice. If you look at fewer dice, that means fewer opportunities to roll a 1. Think about this in chemistry terms. Way back in our iodine clock reaction, we talked about how concentration affects rate of reaction. If the concentration of carbon dioxide decreases, the probability of it reacting decreases. So as soon as I lose some of my carbon dioxide, I will immediately slow down how quickly I lose carbon dioxide, and that continues. What happens to the rate of the reverse reaction? It increases over time for exactly the same reason. I started out with 0 acid, and I gained a whole bunch. Now I have more acid that can potentially react, so I will gain more and gain more and gain more. And I'm the ones that I'm losing. So I didn't lose any to carbon dioxide, and then I got a whole bunch, and now I lost some to carbon dioxide. But carbon dioxide is losing a lot right now, so that gave me a whole bunch. And so when there was more acid, I lost more to carbon dioxide. When there was more acid, I lost even more to carbon dioxide, and that continued to increase. Higher concentration of H2CO3 means a higher probability of reaction. So 1/6 of, let's just call that 6, is only 1 dice. If this is 14, let's do easy math and say it's 12. 1/6 of 12 is I'm losing 2 dice at a time. Here, closer to 18, now I'm losing 3 dice at a time. At 20, I'm losing like 3.5 at a time. At 24-ish, around here, I'm losing like 4 or 5 dice at a time. And then it starts to even out. And here, I'm losing like 5 of my orange dice at the same time that I'm losing like 5 of my blue dice. So the carbon dioxide decreases in rate at the same time that the carbonic acid increases in rate until they both level off at exactly the same rate. The reaction is finished because there's no longer a noticeable change to the reactants, and this is called chemical equilibrium. In this case, the forward and reverse reaction had exactly equal reactivity, which means the equilibrium point was about half and half. And this is where we changed the rules a little bit. In real life, you almost never see two, like the products and the reactants of something have exactly the same reactivity. And so we redid the simulation saying this time CO2 will be favored. What does that mean? We already said carbonic acid is very unstable. That means that carbonic acid is very likely to decay into carbon dioxide. However, carbon dioxide is not very likely to react to form acid. So the way we changed the rules is the carbon dioxide was exactly the same. If you roll a 1, you move it into the carbonic acid container. But the carbonic acid, we changed the rules to roll a 1 or a 2. So anytime one of my acid dice is a 1 or a 2, it gets turned back into CO2 and put in the carbon dioxide tub. If you look at the graph of this, it actually looks more like this. Notice they are no longer converging at 25, but I'm ideally ending with something around 34 carbon dioxides and like 16 carbonic acids. What am I writing? 34. Why would this have happened? Well, when I have 0 acid and 50 carbon dioxide, then the only thing that can happen is that I lose a large amount of carbon dioxide. A whole bunch of these go down here. And so I have like 8 carbonic acids. Now, my carbon dioxide now has a lower concentration, so I won't lose nearly as many as I did last time. But my carbonic acid has twice as much chance to lose as the carbon dioxide because I'm taking 1s and 2s. So when those go up there, you'll notice this slope is not as pronounced as this slope. So I'm losing less carbon dioxide and gaining less acid than I did because it is more likely for me to lose acid than it was before. When I eventually level off, I get to a point where no matter how many times you roll, you will always have around 16 acid dice and around 34 carbon dioxide dice. So did the reaction stop? Well, no, technically, I'm still rolling and losing all of the 1s in this direction. I'm still rolling and losing all of the 1s and 2s in that direction, and that just keeps on forever. But did the reaction finish? Yes, because it's at equilibrium, not equal equilibrium. I will never see more or less than around 34 of those. I'll never see more or less than around 16 of those. Coming back to over how we answered the questions. Did the graph reach a point where it no longer seemed to change? Yes. How is this different from part 1? In part 1, we ended with equal amounts of each substance. In part 2, we ended with more carbon dioxide than carbonic acid. Why exactly is that the case? Carbonic acid is unstable. That means if I had equal concentrations of carbonic acid and carbon dioxide, then the carbonic acid should have a higher rate. So imagine if I had 50 carbon dioxides and 50 carbonic acids, and I'm following these rules, when I roll them, I'll lose like 1/6 of my carbon dioxides, because it's all the 1s, but I'll lose like a full 1/3 of my carbonic acids, all the 1s and 2s. I lose a lot more acid with any given roll because I'm losing a higher percentage. However, we said high concentration leads to increased rate. So, even though these are different numbers, the rate of exchange is the same because carbon dioxide has a fairly high rate due to its high concentration. Carbonic acid has a fairly high rate due to its instability. So, at like 34, I'm losing around 1/6, so that might be 6 dice. At, like 18, I'm losing about 1/3 of 18, which is also like 6 dice. And so you'll forever just be exchanging 6 dice. This is called equilibrium. The equilibrium is favoring CO2 because once everything has settled and stopped moving, CO2 is the thing that we end up with. One of the things that I did in class, let me open back up my spreadsheet, is I wanted to demonstrate that if we did the same activity, but we allowed the acid to start out on top, you would see the data go in the same direction. So let me write my formulas real quick. This one always needs to be, it's going to start here and it's going to lose 1/3 of its numbers, but it's going to gain 1/6 of its neighbor's numbers. So this was our original graph. What would happen if this one started off at 0 and, I need to change this, equals this plus 1/3 of these minus 1/6 of these. Cool. If this one started off, I gotta copy and paste. My graph is broken. That one starts off at 0 and this one starts at 50. Notice that I still end up with blue at around 34 and orange at around 16 or 17. To show you again, this is what happens if it starts off with a lot of blue. I end up with quite a bit of blue. This is what I get when it starts off with a lot of orange. I end up with quite a bit of blue. Why is that the case? Because carbon dioxide is still favored by these conditions. When I have a high concentration of orange, then I will have a high reaction rate because there's a whole lot of them, and it's unstable, so that falls down. Now, I'm still going to have a higher reaction rate for orange because it's unstable and still higher concentration, so it goes down. Here, they happen to cross at exactly the same point. I'm still going to have a higher reaction rate for orange because it's still unstable. So in equal concentrations, orange will lose some while blue is still gaining. And it's only after this point that orange finally begins to slow down. But because the orange is more unstable, at this point at the end, it will have the same reaction rate, remember, about 6 every roll as this one, about 6 every roll. So that was just to show that the reactivity or the likelihood of a reaction occurring is actually what controls your final answer and nothing else. We did one more example in class, but not every period did it, and it's not that important to me. If you have questions about this whole thing, we are going to talk about equilibrium a bunch more. I really like it. And the rest of all these notes, I altered very, very slightly and made it a homework assignment. So if you watch this, great. If you just look through the notes, that's good too. And then the homework assignment is to quickly grasp the next 2 pages and answer these 5 questions at the end. So let me know if you have any questions. That is what we missed in class. Okay, bye.